Hi, this is Tom, and in today's video, we're going to study the law of addition for mutually exclusive events, mutually exclusive events. And mutually exclusive, I'll write it out, and then we'll show you mutually exclusive events. Mutually exclusive events cannot occur together. Okay, so I have a little data set that I'd like to use to illustrate this with. So we surveyed 50 students and we asked them what kind of vehicle do they drive. So the categories for the vehicles were there's people that drove cars, people that drove a truck, people that drove, I'm just going to write SM, and that means either SUV or a minivan, and then those that used public transportation, a bus. And let me give you the data here. The data was 38 of our students drove a car, 3 drove a truck, 8 SUVs or minivans, and 1 person took the bus. Now let's total this. Let's add one more column here. Let's total this. See how many students we're talking about. So let's see, there's 38 plus 3 is 41 plus 8 is 49. One more. So there's 50 students. Now, one thing we can do is let's find some of these. Notice we can find the probability of, I'm going to use C for car and T for truck, S for SUV. So notice this, if I take the probability of a car plus the probability of a truck plus the probability of an SUV plus the probability that they drive a bus, well, that should, if we've done this correctly, that should always total 1. The total probabilities always give us 1. Well, the car, there's 38 out of 50. Plus, the probability of a truck is 3 out of 50. Plus, the probability of an SUV, that's 8 out of 50. Plus the probability of the bus, that's 1 out of 50, and that does add up to 50/50ths. So it does give us 1. Now, notice this. When we talk about a person, how they got to, when we took this sample, what we did is we just asked people, well, what form of transportation did you use to get to school that day? And these were the answers that they gave us. But notice that no one person could be in both categories. You couldn't both drive a car and a truck on the same day. There's no way you can do it. So you can only drive a car that day, or you could only have driven a truck that day, or only driven your SUV or minivan that day, or only been on the bus that day. Because none of these can occur together, we say that these events are mutually exclusive. And let's say I wanted something, let's try something now called OR. I want the probability that maybe I randomly select a person that drives either a truck or an SUV. We'll pick on those folks. They seem to be less environmentally conscious driving trucks or SUVs. Well, if I want an OR statement, it means that I'm content if I randomly select a person that drives a truck or a person that drives an SUV. What I don't want is a car or bus person. When we have OR, the probability of an OR, it's the same as finding the probability that the person drives the truck, and then adding to that the probability that they drive an SUV or minivan. So this is our first law of probability, and that is if we have an OR statement, well, we can break it into addition. And the motivation behind it is is that you could think of this as the number of desired outcomes is the 3 truck drivers plus the 8 SUV people divided by the total outcomes, that's 50. But if you think of fractions, you can split those fractions apart. 3 out of 50 plus 8 out of 50. And that is how we get that law. So if we have an or statement, a lot of people find or means add. Okay? Now let's take a look at something else. If I asked you what's the probability that someone does not drive a truck, so let's do this. Probability that they, or I'm sorry, not, let's do, they don't take the bus. Let's do not bus. I could do that by looking at this. Well, I could get that by saying I could drive a car. That's the probability that they drive a car. It's also the probability of a truck. And it's also the probability that they drive an SUV or minivan. But notice this. If I was to recall this, what if I said, so not a bus is everything except a bus. And so we have a special notation for that, and we call it the complement. And the complement is everything other than, how about this? How about every outcome other than, well, in general we'd say E. In this case, we'd say B. So and what we do is we denote it, so we denote complement E, complement, as E with a bar over it. And notice this, complement, like in the math terms, meaning everything except for that, is with an E. And to say something nice to someone is a compliment with an I in the place right there. That would be, that would be saying something nice to someone. Okay, so if I want everything other than the bus, I could go add up all of those three, the probability of a car, a truck, and an SUV, or I could just say, well, what I want is the is that it's not a bus. So that's the same as saying the car, a truck, an SUV. But let's look at one more thing about this. And notice this. Notice what we said earlier. So the probability of not the bus is equal to the probability of the car, probability of the truck, probability of an SUV. Now, you can add all those up, and it's not too hard in this example. But think of it this way. What if I wanted to find this, another way to think of it is to think of, if I added up everything, the probability of a car, probability of a truck, plus the probability of an SUV, plus the probability of the bus, this is all adds to 1. Well, what if I did this? What if I subtract the bus from both sides? So I have the probability of the car, plus the probability of the truck, plus the probability of the SUV. Well, that's equal to 1 minus the probability of the bus. And what do I have on the other side? We already said that's the probability of not the bus. So the point is that you can use the complement and you can find desired probabilities as 1 minus what it is that you didn't want. So the probability of the bus, well, we know that is 1 out of 50. And so your answer would be 49/50. Now, there's another example. Let me show you this. Let's go to this next page. And I'm going to come back and copy. Here is my example from rolling dice. So let's see if I can just copy that real quick. And let's go over to this new page. Put it right there, and maybe you should make it a little smaller. So an easier way to do this would be, what's the probability? The probability of a sum greater than 2. Well, what does that mean? That means I don't want 2, but I want everything else. I could sit here and count all the everythings, or what I could do is say, all right, if I have everything in the sample space, that's just 1. And the one thing I don't want is the 2, and it's very easy to find that because there's only one of them. So I would subtract 1 out of 36, which is, let me write it this way, so I'd subtract the probability of the 2. And then what I would have is I would have 1 minus 1 out of 36. So that's another way that we can use the complement. So the probability of a sum greater than 2 is also the same as saying the probability of not a 2, everything else. And so to do that, we take 1 minus the probability of the 2, and we're left with everything else. In the next video, we're going to look at what happens when events are not mutually exclusive. Thanks for watching.